It's sort of a kitchen sink example using our expression for the work done by a spring. We have a mass of a quarter kilogram. It's going to fall onto a spring. The spring has a spring constant of 250 newtons per meter, and we're given that the mass displaces the spring down by 12 centimeters before coming to rest for an instant. And we want to find several different things. We want to find how much work is done on the block by gravity, how much work is done in the block by the spring, and how fast was this block moving right before it made contact with the spring. And then what turns out to be the trickier thing to answer is if you double that initial speed, what is the compression of the spring going to be? Which is going to remind us how to solve a quadratic equation. All right, so first part, the work done by the spring. The force of gravity is going to point down, and the displacement of the block also points down. So we can get the work done by gravity as the force of gravity dot product with the displacement, which is just plus mgd, and that gives us the work done by gravity is equal to plus 0.250 kilograms, 9.81 meters per second squared, acceleration due to gravity, and then 0.12 meters. Gives us a work done by gravity to 3 digits, 0.294 joules. Okay. Next part, what is the work done on the block by the spring? And just to backtrack for just a second, make sure that this plus sign makes sense. Gravity is trying to speed up the block, and so gravity on its own would increase the kinetic energy of the block. We should anticipate the work done by the spring is going to be negative and bigger than this because it brings the block to rest and it undoes the work that was done by gravity. All right, so work done by a spring, so something that follows Hooke's law, we worked out is minus half the k constant, spring constant, final squared minus initial squared, and I have some freedom. I'm going to pick this to be my 0 point that I measure distances from. So I have minus k over 2 x final squared minus 250 newtons per meter over 2, 0.12 meters quantity squared. And that gives me work done by the spring is minus 1.80 joules. So an absolute value bigger than the work done by gravity, but it has the opposite sign. All right, next thing we want to get is what is the speed of the block just before it hits the spring. Okay. Well, we have the work energy theorem available to us. So the net work done is the change in kinetic energy, which is K final minus K initial. This final change always means final minus initial in physics. And the block ends at rest for an instant, so the final kinetic energy is 0. And then the net work is I just add these together, minus 1.8 and plus 0.294. That is the net work done. We'll get minus 1.80 joules plus 0.29 is equal to minus a half m v initial squared, which I solve for the speed right before the block hits the spring, and that's going to give me the initial speed is twice the sum of energies, so I got to be 1.51 joules over the inertia, m 0.250 kilograms, and then I need to take a square root. So the speed is 3.48 meters per second, or to two significant figures, 3.5. Okay, now we're going to work through the harder question, which is if I double this initial speed, so that's the initial kinetic energy going into the system is 4 times bigger, what is the displacement of the spring going to be? So let's get ready for a little slog. So the question I'm asking is double initial speed. What is the displacement of the spring? All right, so what do we know? We know that the net work done, which is the work done by gravity and the work done by the spring, is minus K initial, because the block is going to end at rest at any rate. And I know that the work done by gravity is going to be plus mgd, and the work done by the spring will be minus a half k d squared. And on the other side of the equation, I'm going to have minus a half m b initial squared. All right, let me move everything to one side and set it equal to 0, that expression. Let's see what I've got. I'm going to order things a little bit here. Move this term to the other side and multiply everything by that minus 1. We'll have a half kd squared minus mgd. Move that to the other side and multiply by minus 1, minus a half m v initial squared equals 0. So we have a term that's quadratic in D, a linear term in D, and a term that's independent of D. So this is our old friend, a quadratic equation. I'm going to clean it up a little bit by multiplying every term by 2 over k. That's going to give me d squared minus 2mg over k times d minus m over k v initial squared equals 0. And this is a quadratic equation. There's our A, there's a B, And there's our term C. So A is equal to 1, B is equal to minus 2mg over K, and C is minus m v initial squared over K. All right. The two roots for D in the quadratic equation to satisfy D is equal to minus b plus minus. Under the radical, I've got b squared minus 4ac all over twice a. A is just 1. So let me start filling things in. So D is going to be minus minus, so that's a plus 2mg over k, plus minus 4m squared g squared over k squared, and minus 4ac, minus 4, 1 times that, it's going to give me plus 4mv squared over k. And that's all under a square root. And I have a 2. I can factor a 2 out of both of these terms, and then every term, numerator and denominator, has a 2 in it, so that cancels out. So I can get rid of 2, 2, 4, 4 under the radical. So this will be mg upon k plus minus m squared g squared over k squared plus m v0 squared over k square root. All right, we put in values for m, g, and k, and if we double check me on this, I got d is equal to 9.81 times 10 to the minus 3 meters plus minus, this term under the radical is going to give me 0.220 meters. So the two possible values are 0.23 meters and minus 0.21 meters. So it's a quadratic equation. We are going to have two roots. What do those two roots correspond to? Well, going back all the way up here, I'll have the same amount of kinetic energy whether the block was moving up and is stretching the string up against the force of gravity, or the block was moving down initially. Okay, so out of these two roots, 0.23 meters corresponds to, if you work it out, block moving down at 7 meters per second. And then this, the other root, if the block were actually attached to the spring, it would stretch it up 21 centimeters, and that's opposite the direction I picked to be my positive direction. So it comes in with a minus sign. So this is block moving up at 7 meters per second and stretching out the spring. So both physically meaningful, But out of those two roots, this is the only one that corresponds to the problem we're actually solving, of having the block initially falling. There you go.